Good morning, good evening to everyone. Thank you for joining this session. And the topic of this presentation would be about deep learning and GPU acceleration with LabVIEW. Basically, how to make LabVIEW smarter and faster. And during this presentation, we will cover and present two toolkits that have been developed at Ngene. The first one is DeepLTK, Deep Learning Toolkit for LabVIEW, and CuLab, which is a GPU acceleration toolkit for LabVIEW. A little bit about Ngene. Ngene was established in 2015. It is a relatively small company with 5 employees. And Ngene is mainly specializing on developing different technologies based on MNIST platform. And we have developed different toolkits for LabVIEW, and the most popular and famous one is Deep Learning Toolkit for LabVIEW. And CuLab is relatively new, which was released a couple of months ago. And there are a bunch of other deep learning related products, which mainly intended for cover the complete tool chain for deep learning product development. Annotate is annotation tool, and we also have FPGA accelerator for DeepLTK, which is mainly intended for accelerated deep learning inference on FPGAs. Also, we have other toolkits such as beamforming and direction finding toolkit, another hardware product, which is a microphone array for MyRio or SBRio, and very old one, which is locking amplifier for MNIST Rio devices. 2 of our products were winners at NI Week. And in general, we are specializing on deep learning and other signal processing applications, which we are able to implement based on MNIST platform. Okay, so let's talk about the Deep Learning Toolkit for LabVIEW. So it was released in 2017, and it was a winner at NI Week in 2018 in the developer productivity category. And what is deep learning and what are the main features of deep learning toolkit? So the purpose of the toolkit is to provide intuitive high-level API in order to be able to create any neural network models. Sorry. Is it better now? Sean, can you confirm if the voice is better? Okay. So the purpose of the toolkit is to provide API to be able to create custom neural networks and train neural networks in LabVIEW and create create a model which can be later deployed on different targets such as CPU, GPU, or the FPGA. So the toolkit was completely developed in LabVIEW, and it does not have any dependency on third-party libraries or platforms, which allows the toolkit to be deployed for the inference on MNIST other platforms as well, such as MNIST real-time targets or FPGA targets. The toolkit also provides to be accelerated on the GPUs, which is mandatory functionality because it is relatively computationally heavy task, and acceleration on the GPU basically can shrink down the development process from dozens of hours or even days into a couple of minutes. Also, we are providing with large set of reference examples which simplify the process of starting development with DeepLTK Toolkit. So this slide demonstrates the API that is provided with the DeepLTK, which basically provides the possibility to create custom neural networks, build them from the scratch, configure each layer individually, and configure training process, train the neural network, save the trained model, and later load that model for the inference. Also, we are providing some APIs in order to visualize neural network, to understand what is the computational complexity of each layer that is incorporated into the network, in order to be able to analyze and optimize the performance of the network. Also, there are some other utility functions which provide possibility to evaluate the network, manage different resources, and visualize, as I've said a little bit earlier, visualize the network. So the possibilities of the toolkit are defined by the layer supported by the toolkit, and this slide represents what kind of layers are supported with current version of the toolkit and what kind of architectures are supported, such as for image classification, semantic segmentation, object detection, or autoencoder architectures. We will cover these architectures as reference examples a little bit later. So what is the process of creating custom neural networks? So let's assume that we have a diagram which is represented in the upper part, and we want to create this custom neural network. And its corresponding implementation with DeepLTK is represented below. So we are creating initializing neural network and preparing that for the training and specifying different properties, such as what is the size of the mini batch. Then we are creating the input layer, which basically is intended to specify the dimensions of the network. And we are building the network by sequentially adding different layers, sequentially appending different layers to the network. On the upper part, you can see different clusters which are intended to customize each layer individually. So when creating a network during the development process, it's common to create a network in a programmatic manner, but when you have already finished with the training process, you want to have the trained model to be saved in some specific format, so it can be later recreated and initialized, and basically that process should be automated. And the toolkit provides that functionality. And the network topology, or the architecture of the network, is actually stored in plain text format, which stores all the configuration information related to all the layers involved in the network architecture. And the weights, trained weights of the network, are stored in separate binary file. So in order to recreate the network, we would need only to call and read this configuration file and read that binary file, which will initialize the network architecture. So basically, with these two VIs, by loading this network topology configuration file and also weight file, we can basically recreate the network that was built during the training process. The toolkit also provides functionality to visualize network architecture and also display some useful information such as what are the computational complexity of each layer, how much memory each layer requires for storing the weights and storing the intermediate outputs. That information, it might be very useful if you are looking for the optimization and you are looking on how to optimize the network for the performance. And basically with this, from this graph, you can identify the layers which are the most computationally intensive in the network, and understand whether it is possible to reduce by reconfiguring that layer so it can require less computational power or less memory footprint. So for the deployment for the inference, the toolkit provides very simple API. So as we have described earlier, we are using these two VIs, API VIs, in order to recreate the network and basically to recreate the network and initialize the weights. And after that, the network is ready to do the predictions. And before extracting the predictions from the network, we need to initialize the inputs of the network with either the image or some other custom data that was used during the training process, run for the inference, and then extract the predictions from the network as the values from the last layer from the network and display that. As I mentioned, the toolkit supports acceleration on the GPU, and this is very useful functionality as it can speed up the process by up to 30, 40, 50 times. And we haven't been able to test on the latest GPUs, and they are definitely providing much higher performance and we have used for our benchmarking earlier. And we have simplified the process of calling GPU for the acceleration. And basically what is required in order to switch between the CPU and the GPU execution modes, you just need to select device when creating the network. So with the latest version of the toolkit, we have also simplified the process of installing CUDA and cuDNN libraries for GPU acceleration. And once you install the toolkit, and if you have the latest version of the driver for the GPU installed on your machine, it can easily be accessed by the toolkit, like the GPU can be easily accessed by the toolkit to do the computation. Okay, let's talk a little bit about the examples. So the toolkit contains some examples with it, and if you install the toolkit, you can find a set of different examples, like the basic MNIST example, which is designed for handwritten image recognition. It's a classical example, but the main purpose of using that data set for in different examples is actually to demonstrate how to create different neural network architecture, how to use GPU for the training, how to use pre-trained model for the deployment for inference, and basically how to use pre-trained model for deployment on a nice real-time target. There are also some examples on how to train a neural network for object detection, and there is also again, another reference example, which is based on YOLO version 2 architecture, which is designed for object detection for different 20 types of the objects. Sorry. So during this time, we have developed different examples, based on the toolkit for different applications, but we haven't included that into the toolkit because it requires a little bit more efforts in order to maintain that across different versions of the toolkit. So they can be accessed from, and we can easily provide that reference examples to you if you require. So one of them is a signal classification, which is basically designed to classify one-dimensional waveforms. Regression on simple data set, and we have developed some example for inverse kinematic problem, time series prediction, which is based on custom NARX architecture. Image recognition, again, more general version of the image classifier, speech recognition, image segmentation, and anomaly detection. We'll cover a couple of these examples during the presentation. So let's talk about the image classification problem. And use MNIST dataset as a reference and see how we can train a neural network, custom neural network, and use that network for the inference. So MNIST dataset is a dataset which contains handwritten digits in 28 by 28 pixel resolution, and it contains approximately 60,000 images for training and 10,000 images for testing. So to create the network, as we have shown previously, we are using the API from the toolkit. We are creating the network, like configuring the network, specifying which target we are going to use, building the network by sequentially adding different layers, specifying the training parameters, configuring the training process, then iteratively calling the train BI, which will iteratively optimize the network for a specific task. And during the training, we can also monitor the validation error as well. And once the process is finished, we can release the resources allocated for the training, again, with the API provided by the toolkit. We can also make the evaluation of the performance of the toolkit by feeding data set to the toolkit, to the trained model, in order to see what kind of performance this model demonstrates. So let's do some live demo. And this is the reference example that's coming with the toolkit, which can be accessed from the from NICE example finder. And if you navigate to Ngene's folder, open deep learning toolkit section, there are different examples available in this folder. And here we are demonstrating and running this project, which is intended to show how to train MNIST classifier on the GPU. So in order to run this example, you would need to download MNIST dataset, which is basically set of binary files which contains all the images of the dataset in the binary format. And in order to read the dataset, we have developed that custom parser, which is provided with the example. So in order to read the dataset, you should provide the path to the folder which contains this dataset. And if we look into the implementation, we see the section of the code which is actually intended to parse this binary format and extract all the images from the dataset. And basically at this stage, we will have all that 60,000 images with the resolution of 28 by 28. And in order to be able to provide that data set to the toolkit for the training, we need to encapsulate some additional information with it. So basically here we are providing the labels as an array of string. We need to provide the size of the data set. We need to provide what is expected dimensionality of the output. Basically, in this case, it represents how many individual classes are there, and basically the last layer in the network will be of that dimensionality, and each output of each element in the output, and that output would be basically one dimensional array with 10 elements, and each element in that array would represent the confidence level for the one of the specific class. Also, we need to provide what is the dimensionality of our inputs, and in this case, as it is a grayscale image, it will be of 1 by 28 by 28, where 1 is number of channels, as in case of the grayscale images, it consists of 1 channel. Then we are creating DVR in order to be able to effectively manage the memory usage and not to accidentally create a copy of the dataset, because in most of the cases the dataset would require a large amount of memory to be stored. And later the toolkit will access the dataset through this DVR and will effectively manage the memory allocation. And at the last stage, we need to provide what are the ground truths, basically what is assigned class index for each specific input in our input dataset. And if there is a test dataset, we can read the test dataset separately in the same manner. And on the output, we are combining 3 different data sets here, like the train, validation, and test, which are designed to evaluate the performance, correctly evaluate the performance, basically the accuracy of the model based on this data set. And if you do not have a specific data set, like you do not have this data set separated, we are providing the API which will take a portion from the input data set and create some subset of that. So basically, at this stage, we are taking like 5% of our training data set in order to use that as a validation. Okay, so once we read the data set, we can start the building process of our network. We create a network which will be trained with the mini batch of size 128. We are specifying the dimensionality of our network with help of input layer. So basically, it will take the dimensionality from our data set, then by serially adding the layers, appending the layers to the network, we can create our custom neural network. Then we specify what loss function we are going to use for optimizing the network. Then we are configuring the training process before starting the training process itself. And it is provided with help of this VI, which gets as an input the cluster, which selects the optimizer and different optimization parameters such as momentum, like first order momentum, second order, weight normalization parameters, and how the inputs should be sampled from the data set. Then we start the training process, and during the training we are updating the learning rate continuously, and the learning rate update policy can be configured with this interface. And we call the train VI for one iteration and measure what is the current loss and display that. And also during the training process, we can evaluate the performance of the model on the validation data set, and we are using this API. The first one is basically taking the data set and does the prediction and gets the prediction from all the samples in the data set, and that predictions are fed to this evaluation VI, which takes the ground truth from the data set and also the prediction and measures the error and loss values for the current stage of the network. Then after finishing the training process, we can evaluate the performance on the test data set, and we can use other APIs to provide more additional information on the performance of the model. The later part is actually for the inference. So this is for the drawing interface, like we will show that a little bit later. This is basically the section for the inference. So we will get our image from this drawing interface, set it as an input to our network, run forward propagation, get the last layer from the network, and extract the values from that last layer and display that. Okay, so let's run this VI. And as you can see, it will display the loss function during the training process. And if we want also to monitor what is the validation loss, we can enable that like in a manual manner, because evaluating the validation is slowing down the training process. And basically, by monitoring the loss value, we can identify when we can stop the training process. So it seems like we can stop that. And at the test stage, as a demonstration, we can start throwing different digits here and see how the model would perform. Okay, we can stop the test part also. In this example, we are showing which samples in the data set have been incorrectly classified. Like this digit was actually labeled as 4, but was predicted as 6. This was actually 2, but was predicted as 7. And as we can see, like basically these are very hard samples, which might be even difficult for the human to make a correct prediction. And also the toolkit provides functionality to display the confusion matrix, which basically show which portion of a specific class was classified, how it was classified during the inference process. Okay. Let's continue. The toolkit also provides an example, reference example on how to train a model for object detection. And basically, this is a demo which shows a model created for object detection for different types of the nuts. And this demo was completely developed with the help of LabVIEW, and we haven't used any third-party tools to annotate, train, and deploy this model. So, okay, so let's continue. This is the snippet of the code which demonstrates on how to use the toolkit to how to use the toolkit for the inference process for the object detection. Again, we are creating the network, feeding the input, running forward propagation, and getting the prediction from the last layer and parsing that information in order to get the bounding boxes and classification results. The toolkit also supports possibility to create train models for the instance segmentation. And this is another demo which we have created with help of our toolchain. So we have captured these images, annotated them, trained the model, and deployed with help of LabVIEW and only LabVIEW. And in this case, you see how we can use this kind of models in order to localize different objects in the image at the pixel level accuracy and classify them. Another example is anomaly detection, which is one of the most difficult parts. And the purpose of this task is actually to train a model in unsupervised manner, which means that the data set does not contain any annotation information, and train that in a way so it can identify regions in the image which do not look similar to the remaining regions in the image. So as we can see, this region is actually not looking similar to the remaining part. And we want the network to be able to recognize this region and provide basically the location of that image, of that region. And this is very useful task in order to identify different types of the defect during the production. There is also an example for the speech recognition, which is very simple speech command recognition task. And this is a little bit different from the previous example because it is using one-dimensional data such as waveforms at the input, and we need to train a model to be able to classify these waveforms. But we have converted that problem into image classification problem by converting one-dimensional waveform into two-dimensional spectrograms. And once we have created a data set of these spectrograms, we can train classical CNN architecture in order to create the classifier which can recognize and classify different images of the spectrograms, which are basically a representation of one-dimensional waveforms. So in order to cover the whole process of creating neural networks and deploying that, we have created different toolkits and tools which should simplify the process of the development. And we, with help of our toolchain, we are covering the process of collecting and annotation of the data set, the training, We have utility APIs which are optimizing the network before being deployed, and the toolchain provides possibility for the trained models to be deployed on different targets. And another tool which we have developed in order to simplify the development process is the Annotate, which is designed to simplify and speed up the annotation process of the dataset. And it was, again, one of the successful products of Ngene, and it was a winner at NI Weeks in 2019. This is another example or the project where we have used our deep learning toolkit in order to train a neural network. And that network was later converted to other formats and optimized and converted to other formats. So it was possible to deploy that network on other platforms. And in this case, it is a low power and basically solar powered platform, which should be able to do sound classification. And the possibilities of that platform, like the specs of the platform used here, were very limited. And as you can see, the speed of the CPU was very low, and the amount of memory available for using for deploying the neural network again was very low. But we were able to optimize the network with help of our toolkit and deploy that network on so small, low performance and low power platform. Okay, now let's talk about CuLab. This is, as I've told, a relatively new toolkit, which we have released a couple of months ago, and it's intended to accelerate computationally intensive tasks on GPUs in LabVIEW. It was released a couple of months ago, and it is available from VI Package Manager. So this is some fictional code which incorporates some computation, and this is a classical example on how we would implement a specific function with help of LabVIEW. And in order to simplify the process of creating the same function which can run on the GPU, we have created a toolkit that in mind, so it can look very similar. And basically, if you have an implementation of your code in LabVIEW, you can easily port that to be executed on the GPU with help of our toolkit. And its corresponding implementation with the CuLab will look like this. So as you can see, all the functions have been mapped one by one from LabVIEW to the GPU version. And the only thing that we need to add here is actually use the API to push the data from the CPU to the GPU. And after this section, the data will be living on the GPU memory. And after calling this function, we can basically do the calculation on the GPUs. And at the end, we need to bring back the results of this calculation, and which is done with help of this API function. And by the end, we want to release all the resources that have been occupied by this functionality. So basically all the memory that have been allocated on the GPU in order to store our input data or intermediate data, or creating different contexts for doing different computations. All that can be automatically released with help of a call of a single VI. So in order to support like most of the functionality and basically keep the intuitiveness of using this toolkit, we basically planning and already implementing most of the functionality. And as you can see, the function palettes of the toolkit or the API that the toolkit provides is very similar and basically one-to-one mapping to NI's LabVIEW's implementation. So we are providing almost all the functionality from the numeric functions, from the conversion, from the complex, for the functions which are manipulating the complex data, different signal processing functionalities, functions which are working with the matrices or vectors for the linear algebra. We provide the API to manipulate the data stored in the arrays with different dimensionalities and of different type. And also with the latest version, we are trying to provide other numerical operations for trigonometric functions, for exponential and hyperbolic functions. And if we consider another real-world example, which is presented here, like where we are continuously acquiring data from a hardware, and we want that hardware to be processed in line with the data acquisition. So in this example, we are using sound card as commonly available in most of the computers, which is continuously acquiring data from our microphone and feeding that data for the processing. So it is doing some windowing operation, some calculating Fourier coefficients, calculating the amplitude of the spectrum, and doing some kind of conversion to decibel. And if we have this functionality already implemented in the CPU, in order to convert that to the version which can be accelerated on the GPU, the implementation would look like the following section. And as you can see, it is very similar to the CPU implementation. And as I mentioned a little bit earlier, we would need to provide two additional functions which will transfer the data from the CPU to the GPU and do the execution on the GPU device. And at the end, it would need to extract the data from the GPU to be displayed on the CPU part. And by the end, we can easily free up all the resources that have been allocated on the GPU. So we have done some benchmarks in order to understand what kind of performance gain we can achieve on different models of the CPU and the GPU. And basically this graph demonstrate the performance boost. And as you can see, with this initial version of the toolkit, we can gain up to 70 time performance gain, speed up. And also there are newer versions of the GPUs available from NVIDIA, which were released recently, and we are expecting even more speed up when executing on that devices. And I think I have finished with the presentation, and if there would be any questions, I will be happy to answer them. Okay, then. So if there are no questions, thank you for joining to this session. And we will finish this session now. Yes, it seems that there are some questions. Which functions are available for the GPU? Okay, so this slide basically represents all the functionalities that are available with the version which we are going to release soon. So basically, all the numeric operations that LabVIEW provide, and also we can do type conversion on the GPU as well from one type to another type, manipulations with complex data types, some signal processing VIs for the fast Fourier transform, most commonly used functions from BLAS, like matrix multiplication, matrix vector multiplication, and similar stuff. Manipulating the arrays, like for example, indexing and extracting a single element from the array, or replacing subset in the array. And most of the trigonometric, exponential, and hyperbolic functions. So with the official version of the toolkit available, these last functions are not available, but we are going to release new version which will make this functionality available. Okay, there is another question. How does CuLab differ from the NI-GPU toolkit? Yes, so NI-GPU toolkit is a great one, and basically we were motivated from that toolkit as well, but using that toolkit requires a little bit additional coding in order to allocate different resources on the GPU for different types of the data and initialize different functionalities such as FFT, and basically with help of our toolkit, we first tried to simplify this process, as you could see from different examples. And also a nice toolkit, a nice GPU toolkit does not cover the whole functionality represented in this slide. So it has, out of the box, it has some functionalities to perform FFTs and BLAS operations, basic linear algebra operations. But if you want to have some custom functionality, you need to go and implement that first in the C, convert that to the DLL and call the DLL from LabVIEW. And with help of our toolkit, and what is the main difference from NI's version is actually we are providing all that required functionality out of the box, which is, and we hope is, should be very easy to use. Okay. There is a question about how DeepLTK is compared with other famous deep learning frameworks such as TensorFlow. To be honest, we haven't done this comparison. like we have done one or two comparisons. We have seen similar performance, but we haven't done thorough analysis on different architectures and this kind of stuff. I understand this concern, but we haven't done this so far, and if it is very important and very useful for the audience, maybe we'll do that later and provide that kind of comparison results. But what I can say, like all the toolkits and frameworks are using basically under the hood, they are using the same CUDA and cuDNN toolkits from NVIDIA, and from that perspective, either our toolkit or other frameworks should provide similar performance. Okay then, thank you very much. Thank you. Thank you for the participation and sharing your time with us. And we're always available, and you can contact us. And if there would be any questions related to one of our toolkits, we will be happy to answer them and collaborate with you and try to help you to solve your problems. Thank you very much and take care. Stay safe. Bye-bye.